right, I wanted to further illustrate how the pressure force is perpendicular to the area over which the force is acting by taking a look at a problem which we have a boat that's floating in water. And so let's say that you drill a hole in the boat here. Then I think most of you can say that you know which direction the water is going to go. It's going to go perpendicular to that surface at that point. If you drill a hole here, the water will shoot in that way. If you drill a hole down here, the water will shoot up that way. So it should make sense that that's the direction of the water flow if the forces are perpendicular to the surface. Okay? And if they weren't, then the water would be shooting off in some other direction. So this shows that that's the case. And so why is that the case? Well, because any component of the force that comes in at an angle is then compensated for by sideways forces of the water, which will tend to cancel that out. And so all that's left then is the vertical component of the force. And that vertical component is the one that's perpendicular to the surface. So let's say that you might say then, well, okay, great, but why is it that you're only getting force from above, or that you're getting force from above and below, but not just from above when you're holding up the weight of the atmosphere? And so the way that I'd like to try to illustrate this is, let's just imagine what's causing the pressure for a second. Here's your head. And so you've got a molecule coming in from this direction, then bouncing off. Got a molecule coming in from this direction, bouncing off. And these molecules are moving pretty fast. They're moving typically in a normal room temperature situation. The air molecules are moving faster than the speed of sound, maybe 500 meters per second or 1,000 miles an hour. They're coming in, slamming into you, and bouncing off. And because it's a statistical thing, you've got as many molecules coming in from this direction, because there's so many of them hitting, you're not just having them come in from one direction and then go out, but they're coming in from every direction, every conceivable direction, such that there's no preferred direction, but rather the force is kind of evenly distributed over the entire surface. Because remember that this is a change in momentum, and the force that's exerted here is equal to dp dt, the derivative of the momentum with respect to time. And then you have to exert an equal to opposite reaction force to prevent the surface of your head from imploding inward. But that's what causes those forces, are a bunch of these little tiny collisions between molecules that are just as likely to hit you from above as below, from the left as from the right. And so that gives you that average value for that squeezing pressure that you're feeling. But let's say that you're in an airplane and somebody lights up a cigarette and say, some joker says, hey, that's no good. So he goes and he opens up the emergency hatch. Let's say that you could do that. I don't think you can, but let's say that you could. Okay, and so that door opens. Let's say it's this door here. And so he blows the hatch. Okay, and so now the molecules are going to want to go out. Okay, because this is low pressure here. This is high pressure in here. So you got lots of molecules going this way and very few molecules going that way. So the high pressure molecules are colliding more times per second than in the low pressure area. And so the pressure tends to move from high to low. And so now the forces acting on your body are basically all coming in from the same direction. Okay, and so what this is going to tend to do then because there's very little, maybe just a couple of collisions from this direction, but not enough to compensate, is that you're going to get sucked out of the airplane. Okay? But we don't like the word suck in physics, and so we say instead that you're being blown out of the airplane because of the fact that you have a preference for collisions that take the air from higher pressure to low pressure than you do from molecules that'll still be there, but not nearly as often. That will tend to move in the other direction statistically. You'll get a couple of flukes that'll go this way. But most of that pressure is acting just on one side of the object, which then blows you out. Okay? And so that's the reason why you don't want to open up the door in a pressurized air cabin. Okay, so with those ideas in mind, hopefully you have a better concept now as to what causes the pressure force. What I want to do now is an example. Let's say that you're driving along on a mountain road and your car's handling great, but then at one point you just make one little tiny mistake and accidentally drive off the side of the road, down this embankment, and into a lake. Okay, and then you go to the bottom of the lake and you're 10 meters down. And it's a brand new car, so you're quite astonished at first to discover that your radio is still working, but then after a short period of time, just shorts out. And so you go, well, I better get out of here. So you try to open up the door. So here's the door, let's say. And so you're going to have some forces acting from the outside. And so that outside force then is going to be equal to P total times the area of the door. And let's assume that we're talking about the P total as being to the midpoint of the door, which is, and the midpoint, let's say, is 10 meters down. I already figured out that this is 2 atmospheres pressure at this point, pushing from the outside. So P total will be 2 atmospheres times the area of the door. The area of the door, let's say, is 1 meter by 1/2 meter. Something like that. Okay? But then there's also a force from the inside that's just equal to P atmosphere times the area. Now remember that those forces are always perpendicular to the surface. Okay, so that means that the larger force is coming from the outside, and so when you try to apply a force, the force of the person, you notice that it's not doing much good. Okay, and so here F person plus P atmosphere times area has to be greater than or equal to P total times the area. Okay, and so therefore the force of the person must be greater than or equal to, now here for P total, this is going to be P atmosphere plus rho G y times the area. Minus this term, which is brought over to the left-hand side, P atmosphere times the area. So the P atmosphere times the area terms cancel, so the force that's exerted by the person must be equal to rho Gy times the area of the door. Rho, 10 to the 3 kilograms per cubic meter, times G, 10 meters per second squared, times Y, 10 meters, times A, area of the door, 1/2 meter by 1 meter. So that'll give us 5 times 10 to the 4 newtons. Okay, so remember this is pressure times area is force. Okay, so this is P total times area, that's force here, and there's a force on the inside, and so that's 50,000 newtons which is approximately 10,000 pounds. So you'd have to be able to exert 10,000 pounds worth of force in order to open up the door, or something in the order of that. And so if you could do that, then you could just punch a hole right through the door, which would probably be a better idea, because you need to equilibrate the pressure. You can knock out the window. That would be a good idea to do. If you have one of those little sharp, pointy metal things, you can use it to knock out a portion of the window. Or if you really want to get serious about it, you might be able to put your back up against the front seat and push out the windshield. Okay, but you're going to have to do something unless you've got regular crank windows, and of course you could just lower the window, but your electric windows are probably not going to work. So you need to equilibrate the pressure from the inside to the outside. Then your door is probably going to be too warped to open, but you still might be able to get out through the window and then swim to the surface. Still highly dangerous, though, so not something that I recommend unless it's a life-threatening situation. I wouldn't just try it for fun. They did it once on 2020. The guy who went into the water had 3 lifeguards around just to make sure he'd be fine, and he still broke his arm. So, it's a dangerous thing to try. Okay, but this shows us how much pressure there is at even a relatively modest depth. The next thing that I'd like to talk about is buoyancy. Okay, so buoyancy is an upward force that acts on an object that's immersed in a fluid. And so we could try to figure out what the buoyant force would be, say, for a massless cube that is submerged beneath the surface. Now, if any of you have ever tried to take, say, a beach ball and swim down to the bottom of the swimming pool with it, you know that this is not an easy thing to do. And the reason for that is the buoyant force. And so let's see why that buoyant force is there. Okay, so here we're not going to worry about the mass of the cube. We're going to make this a massless cube that is just L by L by L on a side. And let's find the buoyant force on the cube. So we're going to have a force from above. That force from above, F, I'll call it F down here, is going to be equal to the total pressure, which is P atmosphere, plus rho g y. Let's say the top of the cube is a distance y beneath the surface. Okay, so this would be multiplied by the area, A. And the area here would be the area of that top face, which would be L squared. The force acting from below, which I'll call F up, is equal to P atmosphere plus rho g times, and the depth here is not y, but y plus L. Because it's an extra depth L beneath the surface. And so that's all then multiplied by A, which is the area of this lower face. But because we chose a cube, the area of the lower face is equal to the area of the upper face. So now we can find the difference in force, and that should be equal to the buoyant force, because all the sideways forces should cancel. So F net is the buoyant force. So that'd be F up minus F down. Or FB is equal to P atmosphere plus rho G times Y plus L times A minus P atmosphere plus rho G Y times A. Okay, and so we can multiply all these terms out. This gives us P atmosphere times A plus rho G Y times A plus rho G L times A minus P atmosphere times A minus rho G Y times A. So we have quite a few terms, but almost all of them cancel. Here's a plus P atmosphere A. There's a minus P atmosphere A. Here's a rho G Y A minus rho G Y A. So all we're left with is this middle term, which is rho G, that LA is just L times L squared, or L cubed, but that's the volume. Okay, so LA here is the volume of the cube. Okay, so the buoyant force then is the density, is this the density of air or water? This is the density of water times G times the volume. And so this is just the mg for the fluid displaced, the weight of the fluid displaced. Okay, so m is density times volume, but this is the mass of the fluid that would have been there if the cube weren't there. Or the mass of the displaced fluid. So if we pretend that the mass of the fluid is still in there, then there'd be no forces on this cube, right? Because it's a massless cube. But we take that away, and that must be the imbalance now in forces, which is the weight of the fluid that isn't there anymore. There's more pressure pushing from below. There's more forces that are associated with the pressure, I should say, pushing from below. We don't want to say that pressure is a vector. It's an easy mistake to make. But the forces are bigger from below than they are from above because there's more pressure driving those bigger forces that are perpendicular to the area. And so that gives rise then to a buoyant force that's equal to the weight of fluid displaced. Okay, so with that idea in mind, let's take a look at an object that's floating. What kind of an object could we have that's floating? Well, how about a big chunk of ice? We talked about ice before. So let's have a big cube of ice that's 10 meters by 10 meters by 10 meters on a side. Now, you've often heard about the tip of the iceberg, and that's an expression that relates to the fact that there may be a lot more going on beneath the surface. You know, and so that's an analogy to things that could be happening, say, at a murder mystery or something. But here, if we say that we see a little bit of ice sticking up above the surface of the water, then what we're going to see here is that that tells us there's a lot more going on beneath the surface. Okay? There's a lot more ice beneath the surface, in other words, that buoys up that portion of the iceberg that is beneath the surface. Okay, and so here then, let's find that portion of the iceberg that is above the surface. and so we could call that here our, let's call that y, and then this total height here is 10. Okay, and so if this height here is y, then this distance here we could call x. That's the amount that's submerged beneath the surface, so that x plus y equals 10. Okay, so how do we figure this out then for a floating object? Well, first of all, we have to realize that we're in static equilibrium. So in static equilibrium, that means the forces must balance. So we have the weight of the cube is the downward force. That has to equal the buoyant force acting upward. Okay? And so the weight of the cube is pretty easy. That's just equal to the mass of the ice times the acceleration due to gravity. But the mass of the ice wasn't given in this problem. But instead, let's say that we're given the density of the ice is equal to 0.9 times the density of water. Okay, so that's about right. It depends on the type of ice and what the temperature that it's frozen at is, but the density is roughly on that order of 90%. Okay, so the mass of the ice then is going to equal the density of the ice times the volume of the ice, which is going to be 10 meters by 10 meters by 10 meters multiplied by g. Okay, and so that's the weight of the cube. What's the buoyant force? Well, the buoyant force is the weight of water displaced, and so that's not the whole volume of the cube, but rather it's equal to the density of water times the acceleration due to gravity times the volume of water displaced, which is going to be 10 meters by 10 meters by x meters, okay? Because x is how far it's sunk down into the water until it displaces enough weight of water to equal the weight of the cube. Okay, so that is the physics of what we're trying to show here, is that that value of x is really what we're going to need to solve for. Because we're in static equilibrium, we set those two equal to each other. That gives us the density of water times the acceleration due to gravity times 10, I'll drop the units here, 10 times x equals the density of ice. Now instead of figuring it out and plugging it in as a number, let's just write it as 0.9 times the density of water. So that's 0.9 times the density of water times 10 times 10 times 10. The reason for doing that is now we have common factors of the density of water on both sides of the equation. We've got common factors of g on both sides of the equation. And we've got common factors of 10 on both sides of the equation. And so x then is equal to 0.9 times 10, or 9 meters. So the distance that it's submerged is 9 meters, and so therefore y, the height that's above the water, is going to be 10 minus x, or 1 meter. So we just have a little tiny bit of the iceberg is above the surface, just 10% of it, and 90% of it is below the surface.